Let's talk about entropy. So imagine that we're given two states, state 1 and state 2. You can imagine that these are drawn on a PV or a TV diagram. All I mean by having them be distinct states is that they don't have identical properties to one another. And let's imagine that we go between these two states using a set of reversible processes. So for example, process A goes from state 1 to state 2, and it's reversible. Process B also goes from state 1 to state 2, and it's reversible. Clearly, the way I've drawn it, though, the intermediate states between states 1 and 2 must be different from one another for process A and process B. Alright, that's all we're thinking about. We'll also draw in a process C that goes from state 2 back to state 1. Okay, these are the three processes that we're going to consider for the argument I'm going to make about entropy. Now, you can imagine that if you have a particular system that's undergoing one of these sets of processes, you can start it here in state 1, and let's say that we want to go to state 2 and then back to state 1. We want to actually execute a cycle. So let's take process A to get to state 2, and then process C to get back home to state 1. That was a cycle because we ended up back at the place we started, okay? So what can we say about that cycle that relates to entropy? Well, we don't know a whole lot about entropy yet, so one thing we can write is that going along process A, the integral from 1 to 2 of delta Q over T for process A represents this part of the trip. And if we add that to the integral from state 2 to state 1 now of delta Q over T for process C, then remember, we've just executed a cycle, and we learned a few lectures ago that the integral of delta Q over T across all boundaries and all times in a cycle is minus sigma cycle. But of course, we have reversible processes, so if you have a reversible cycle, sigma is 0, there is no added entropy, so that means that the sum of those two integrals has to be 0. Again, all I did was trace out two integrals, one representing the process A, one representing process C. The sum of those two has to be 0 because it's a reversible cycle. Okay, let's make the same argument now for process B and process C, going from state 1 to 2 and then back. So if we do that, we go through process B, through process C to get back to state 1. Well, using exactly the same logic, we can write down a sum of two integrals for that, right? It's the same setup, the only thing we've done is switch the subscript on A to being a subscript B. Okay, why did I do that? Well, we know that both of these are equal to 0, so what happens if we actually take our second equation and subtract it from the first? We can do that, no problem. So we do that, and we get that the integral of delta Q over T for process A minus the same integral, delta Q over T for process B, is 0. So actually, that means that the integral of delta Q over T for A is equal to the integral of delta Q over T for B. That's interesting. Let's think about what that means. It means that each of those integrals that we dealt with up above must be path independent. And by path independent, again, I'm not thinking of like a physical displacement necessarily, but a path through a PV or a TV diagram. So you could imagine going from state 1 to state 2 this way. Watch the star. Oh, it's going crazy. It went up into the title, and then it comes back down to state 2. Even that integral would be equal to the integral from 1 to 2 of delta Q over T for A or B or any path that goes between 1 and 2 as long as it ends up hitting both of those endpoints. Given that apparently these integrals are not path dependent, they're only dependent upon the endpoints, we can actually define a property associated with the value of one of these integrals, and we call that the entropy. So delta big S, which equals S2 minus S1, is the integral from state 1 to state 2 of delta Q over T for some internally reversible process that goes between those two states. For now, we are just talking about internally reversible processes. Eventually, of course, we'll generalize entropy to dealing with irreversible processes where it's really more interesting. And just to address one potential misconception, the value of this integral, generally speaking, is not guaranteed to be 0. Remember, this integral is only equal to one of the two terms in an equation like that up above where you're dealing with a cycle, but it's one of the two terms in the cycle. Generally speaking, those two terms cancel each other out, but each term is non-zero. Otherwise, it would be trivial if this integral was always 0, and if delta S is always 0, that's not very exciting. But indeed, delta S, generally speaking, will not be 0, even for a reversible process. Okay, so let's use this. We'll bring that up there. And I'm going to rewrite this in a way that may seem strange, although you have to get used to this for the next few lectures. Let's rewrite delta S as the integral from state 1 to state 2 of ds. Now if I do that, and you can see that I'm going between the same two states on both sides, I can actually drop the integral signs and just illustrate the relationship between the differentials ds and delta Q. Okay. So now if we further assume that we're dealing with a system where kinetic and potential energy changes are not important, so that delta Ke equals delta P equals 0, then remember energy conservation for a system like that, if it's a closed system, is just delta big U equals Q minus W. Now let's rewrite those terms in terms of integrals. So delta big U becomes the integral of du, Q becomes the integral of delta Q, W the integral of delta W. If you forgot why we use these inexact differentials delta, you can look in your textbook for that detail. It's not particularly relevant for what we're doing here. We can drop these integral signs too. So now we say that du equals delta Q minus delta W. And we know that W is the integral of p dv, so that must mean that delta W is just p dv, right? That's the relationship between those differentials. So we can substitute that into our equation for du. Du becomes delta Q minus p dv. Move that up. Next step will be to substitute in something for delta Q. Well, if we're talking about an internally reversible process, which is all I've been talking about on the left, then we can just use this expression at the top, right? We can rearrange that for delta Q. Delta Q would just be T ds. So let's do that and sub in for delta Q. So if we do that, T ds equals delta Q, and du equals T ds minus p dv. Now technically we're done, but I'll rearrange this into a more familiar form, namely that T ds equals du plus p dv. And of course you can divide this entire thing by mass to get the specific version, which is T d little s equals d little u plus p d little v. This is one of the fundamental equations of thermodynamics. It relates temperature, entropy, internal energy, pressure, and volume, and we'll get some practice using it over the next few lectures.